First day of the workshop. So the first talk in this session, Avishay is going to be talking about his exciting recent work with round-RAS, solving a long-standing open problem with quantum complexity. And there's going to be something in this talk even for those of us who are classically inclined.
Thank you. So this will be mostly a talk about lower bounds. This is an Oracle separation of BQP and polynomial hierarchy, joint work with round-RAS. And this beautiful illustration was drawn by Kevin Hong for Quantum Magazine. This tries to illustrate an oracle where you sort of click on this button and it gives you like an answer. And so let's start with recalling some of the favorite complexity classes. So we have P, we have NP, co-NP, and all of these sits inside what is known as the polynomial hierarchy, which can be captured by alternating quantifiers, and we will see the exact definition in the next few slides. And all this sits within P space, right? Everything that you can compute in polynomial space. We can also talk about randomized algorithm. One favorite class is BPP, bounded error. This extends P, but we suspect that it actually equals P. However, currently we only know that BPP is inside, at least in this picture, inside PH. And the main motivating question for this talk is where does BQP, or bounded error quantum polynomial time, sits within this picture? So we know that anything that a randomized algorithm can do, a quantum algorithm can do. And we know that BQP sits inside P space. So it's somewhere between BPP and P space. But we want to know more. So in particular, we want to know what is the relation of BQP with NP or with PH. We suspect that these two things are incomparable, that there are some languages that are in one and not in the other, and vice versa. However, we cannot even separate P from P space, right? In this picture, it could be still possible that everything equals to P, right? So any separation that we will try to prove should be in some relaxed notion, and we are very far from proving that P is not equal to P space, so we will relax the question. Okay, so we will talk about oracle separations. And indeed, oracle separations were known with respect to BQP. So this gives us some evidence about the relation between the true classes. Maybe not the right evidence, but some. So in particular, this result that shows that there exists some oracle where NP is not in BQP with respect to this oracle can be thought as saying that it's highly unlikely that quantum algorithm would solve NP-complete problems, or that would solve the SAT algorithm. We can base it on this oracle separation. This fundamental work of Bernstein and Vazirani that actually introduces BQP also proves that BQP is stronger than BPP with respect to an oracle. So there exists some problem that you can solve in BQP with access to this oracle, but you cannot solve it with BPP with access to the same oracle. Okay, so this already gives us some quantum superiority, or and you can ask whether it holds for higher classes. So maybe you can do it for NP, and in fact it's correct, and you can even do it for MA. So Watrous showed a separation between BQP and MA. And this was the state of the art. It was still open to show such a separation for BQP versus PH, and even BQP versus AM, something that sits even lower than the second level of the hierarchy. This is what we will do in this talk. So our main result will be a separation of BQP and PH. So let's recall what is PH, what is the polynomial hierarchy. So we say that a language is in the polynomial hierarchy if there exists some constant k and a sequence of quantifiers. There exists y1 for all y2. So we have these alternating quantifiers, and x is in the language if we can write this formula with these ky's and then apply some relation r, which is polytime computable in its argument, on x and all these y's. Okay? In particular, you can think of NP is a version where you have only one quantifier, there exist. Okay? And then you have a relation on x and the witness. Co-NP is for all, and this sort of captures both of them, and you can alternate between the quantifiers. Okay, so what do we want? We want the relation to be polytime computable, and we want the strings, the y's, would be of polynomial length in the length of x. what we show, our main result, we show that there exists an oracle under which BQP with respect to this oracle is not contained in pH with respect to this oracle. So really what we do, we come up with an oracle and a language that can be computed in BQP with queries to this oracle, but cannot be computed with pH with queries to this oracle. In fact, the result is stronger than that, and we can allow even a super constant number of alternation, and we can even go for y's which are of size nearly exponential in x. So, and we have some trade-off between these two things, but I will not get into the exact details here. You can just think of k as constant and the sizes of y's as polynomial in the size of x. Okay, so I mentioned oracle, but actually I will focus most of my talk on this black box model or the query model. And the reason that it's enough is that black box separation imply oracle separation. So we can sort of take the separation from this world to the oracle world. And these are known reductions. And what is this black box model or the query model? So think of your input x as given to you as a black box. And you want to learn some property of the input. What you can do, you can sort of ask this black box what is the value of a specific coordinate. Okay, so you give it a coordinate I, and it gives you the bit of the string in this location. Okay, if you want to think of this maybe as a function, you can think of it as like you give it some input and it gives you some output. Okay, so when we talk about deterministic algorithm with respect to this model, this really corresponds to the decision tree model, right? The decision tree depth is exactly the number of queries that we make to this to this black box in the worst case. But we can also talk about randomized version, non-deterministic version of this model. And in particular, we will think of quantum version of this model. This was studied a lot in the literature. What do I mean by that? So instead of just giving one query, like deterministically, I would give a query in superposition, and then I will get an answer in superposition. So I have a different coefficient for each of the possible queries, and then I get the value of xi multiplies this amplitude by -1 if it was a -1, and doesn't change it if it was a +1. Okay, so this is one way to define the query model. And a lot of the results in quantum computing are actually presented in this model. So you can present Rover search in this model, period finding. Okay. What is the analog of pH in this model? The analog of pH, and Avi mentioned it already this morning, is AC0 circuit. And why do we have this correspondence? So think of this quantifier. We can take the exists quantifier and change it with an OR, feeding many inputs, and we can change the for all with an AND. And we need to change the relation, so we can change it with a small DNF. So basically, whenever we have an expression that defines a language in pH, we have an AC0 circuit. And the depth will be really the number of quantifiers in this expression, or maybe +1. Okay, so really what we want to show is we want to show some separation between quantum query complexity and AC0 circuit. And then we can sort of use the non-reduction to translate them into oracle separations. Okay, now I want to move to the pseudorandom setting. So Kaveh mentioned it in his talk a lot, so I will just go over it briefly. So on the right-hand side, we have a truly random string. So all these coins are fair and they're independent of one another. Each is heads with probability half, tails with probability half. On the left-hand side, we have a pseudo-random string. Okay, so a string that looks random. What do I mean by that? I mean that it looks random to the function f that is operating on this sequence of bits. Okay, so to be more precise, we say that the distribution is pseudo-random against a class of function c. If any function in this class c has a similar expectation under the distribution d as it has under the uniform distribution. Okay, meaning, in some sense, the function cannot tell apart between the two cases. Okay, so this beautiful two works show that pose this challenge. Can you find a distribution which is pseudorandom for AC0, but not pseudorandom against polylog-time quantum algorithm. And here I really mean in the black box setting. Okay, so the algorithm would work in polylog time and would make queries to the input. Suppose that you can find such a distribution. They show that you can translate it into an oracle separating between BQP and the polynomial hierarchy. Okay, and the connections are, like I mentioned, like them vaguely at least, the connection between pH and AC0, and the other connection is just by sort of padding argument, you can think of it. Okay, so I will not go into this reduction, but let's just focus on this question. So now we are focusing on this question on pseudorandomness. We want to find some distribution that look random for any constant depth circuit, but doesn't look random for a quantum algorithm running in polylog time and making even less than that number of queries. In fact, our algorithm would make only one query to the input. Okay. So I want to define the advantage of a distinguisher. So let's say that I want to distinguish between the left-hand side and the right-hand side. And I have some algorithm A. So I say that an algorithm A distinguishes between the two with advantage alpha if alpha is exactly the difference between these two expectations, or the difference between the probability that AX equals 1 and the probability that AX equals 1 on D, or it equals 1 on U. Okay. And what is our main result? We present a distribution D such that there exists a log n time quantum algorithm making one query to the input that distinguish between D and U with advantage at least 1 over log n. Okay, so these are distribution over strings of length 2n capitals. We also show that any quasi-polynomial size constant depth circuits can distinguish between D and U with advantage which is at most 1 over square root n. So there is a gap between the two. This gives you advantage which is 1 over log, and this gives you something which is much smaller than that. And in fact, you can even amplify it via standard techniques, so you can make this advantage to be a large constant as you want, and you can even make it close to 1. So you can make it polynomially close to 1, and this we do sort of like afterwards. Yeah?
Is there a reason for which it's 2n and not n?
It will be just more convenient for the notation in the rest of the talk. So yeah, now it doesn't make sense. Why did I pick 2n? Yeah, I don't want to change like the notation. That's each time. Yeah. Okay. And once we have this, we have the oracle separation via these previous reductions. So my plan for this talk is to first describe you the distribution D, then to show you very briefly, tell you why a quantum algorithm works in distinguishing this distribution from the uniform, and then the hard part and most of the talk would go into showing the lower bounds, going to show that this second bullet, that constant depth circuit cannot distinguish between these two distributions. Okay, so let's start with the definition of the distribution. So this is based on Aaronson Forrelation distribution. I will first describe you some Gaussian distribution, and then I will describe you some distribution over Boolean strings. Okay, so again, we have this capital N, and we think of it as a power of 2. And we pick epsilon. This will be some parameters that will be more clear later. We pick it to be 1 over log n. Okay, we take some multivariate Gaussian distribution over a space of dimension 2n with 0 means and covariance matrix, which looks like this. So it's a block matrix. It's a 2n by 2n matrix, and I have 4 n by n blocks. So the first block is just the identity matrix. The second is the Hadamard matrix, Hadamard identity. And I multiply everything by epsilon for some reason that is not clear correctly. What is this Hadamard matrix? It's a fairly used matrix all over the place, but especially in quantum computing. So this is simply the matrix where the ij entry equal to 1 over square root n minus 1 to the inner product of the binary representation of I and j. Okay, so you think of I and j as numbers between 1 and n. They have log n bits, and I'm just thinking of these bits as representing vectors. I'm taking the inner product of these vectors. Okay, so this gives me some distribution over the reals, right? Over vectors over the reals. And now I want to sample some distribution over strings, over vectors over plus minus 1 to the n. So the idea is to first sample z according to g. And then it will be very convenient that all the coordinates will be within minus 1, 1. So what do? I simply truncate them. If it's smaller than minus 1, I take it to be exactly minus 1. If it's between, I don't do anything. If it's higher than 1, I replace it with a 1.
So the epsilon is chosen so that this will be rare.
Exactly. So now you see exactly why I chose epsilon. I chose epsilon so that this would happen. This would change something with very small probability. So I picked it so that this will be, let's say, with probability 1 over poly n. Okay, so we can sort of like forget about this truncation. It would not affect anything. And then basically we have numbers between minus 1 and 1. So how should we think of them? We should think of them as biases of coins, and then just flip these coins independently. What do I mean by that? So for each I between 1 and 2n, I have this number, zi. It's just a number between minus 1 and 1. So I will pick z prime I to be a plus minus 1 random variable, where the expectation of z prime I should be exactly zi. What does it give me? So if the zi was 0, then I flip a fair coin. If it was a 1, I always answer 1. If it was, let's say, a half, then with probability 3/4, I would put a 1. 1/4, I would put a minus 1. And I do it independently for all coordinates. Okay, so this is a distribution. I want to say an alternative way to define G, which would be useful. So this sort of, I didn't really tell you, maybe such a distribution does not exist. It's not clear. I just tell you what the covariance matrix. So let me tell you a different way to define it. So you can sample x1 to xn to be Gaussians with mean 0 and variance epsilon, and pick them independently now. And then take y1 to yn to be simply the Hadamard matrix times x1 to xn. And z will be simply, the concatenation of x and y. Okay, so this is, if you do this process, then you would get that the variances are epsilon and the covariances are epsilon divided by square root n. Okay. So now, as I mentioned, Scott came up with this Forrelation distribution. You can also, so the name Forrelation comes from correlation of the Fourier. So it's like you applied, you can think of them as like two parts of your input. So if you apply the Fourier on the first part, you would get something that is correlated with the second part. Okay. And he came up with this distribution with an algorithm at hand. So with the distribution came an algorithm. Basically, this is a fairly simple algorithm. Yes?
If you replace h by 0, then it's basically a uniform distribution?
Yeah.
Then
yes.
Nothing will work.
Right. So I want a distribution such that quantum would catch it, but classical algorithms would not.
So h will make the quantum thing work.
Yes, exactly. Yeah. So the distribution h was in order for this next slide to work. So for this quantum algorithm to work. So there is a fairly simple quantum algorithm that takes one query, log n time, and accepts an input x, y. So think of now of the input as fixed and the probability over the randomness of the quantum measurements. So the probability that Q accepts is 1 plus phi of xy divided by 2, where phi is this expression. So I'm summing over I, summing over j, taking the Hadamard thing, so this should look familiar, times xi times yj. Okay, so what is this? You can think of it as just, so notice that this is a multilinear polynomial of degree 2. Right? And we can sort of analyze what is expectation is with respect to the uniform distribution and with respect to the distributions that we just defined, D. So what happens under the uniform distribution to this expression? We have all these bits. They are independent of one another. So in particular, what happens with respect to what Amir was suggesting? So each of these xi, yj are uncorrelated, and each of them are like fair coins. So the expectation of this monomial will be 0, and then we can use linearity of expectation to say that the expectation of this entire thing is 0. Right? What happens under the distribution D? So what is the expectation of xi, yj? It's exactly this plus minus 1 to the, minus 1 to the ij, divided by square root n, maybe times epsilon. So basically the plus minus 1 cancels with the expectation here, and we get a positive sign for each monomial. And then we sum all of them up. We have n squared of them, and we basically get epsilon. Okay. So it becomes very simply epsilon. So, okay, so under G this would be epsilon, but we are talking over D, so we need to worry about this truncation, so it's almost epsilon. Okay, so this is the only thing that is a little bit annoying, but okay, so what did we get? We get a quantum algorithm whose expectation under the uniform distribution is half, right, because it's 1 plus 0 over 2. And under the distribution D is something like 1 plus epsilon over 2. So we get an advantage epsilon. Okay. And epsilon is 1 over log n as promised. Yeah.
Is the Gaussian really necessary? If you just do random independent plus 1 minus 1 instead, like does the analysis become much hairier?
So yeah, so actually the original suggestion of Scott was a little bit different. We changed it a bit, but mainly towards the second part of the talk. So a lot of things that you would like play with them would still work for this part. Not sure about the second part. Yeah, so the Gaussian is well, you define it with Gaussian, but it's really important also that you would pick them as biases of coins for the second part to work. So one thing so the variant that Scott suggested was to just take the Gaussians and take the signs. Okay, so this would give you also a discrete, a distribution of discrete objects. I don't know how to analyze this. Okay. So I can just very briefly tell you how the quantum algorithm looks like. So basically, you have only one query. So what can you do? So you query in superposition over all possible positions, and then you get the answer. You apply the Hadamard transform on the left part, and then you sort of measure in the right basis, and this would pop out. So this probability would be the probability of getting a 0, and 1 minus this over 2 will be the probability of getting 1. So it's fairly simple, like few lines of calculation, not something too complicated. But we are in a semester on lower bound, so I want to focus more on the lower bound part. Okay, so I want to tell you more about why is D pseudorandom against AC0 circuit. Okay, so these will be the highlights in the proof. So the proof would use Fourier analysis. I will crucially use the fact that AC0 circuits are well approximated by sparse low-degree polynomials. And this, you should put emphasis here on the sparse. And this is very similar to the notions that we had in Cavet's talk. Okay, so this bound on the coefficient of sets of size k. So this would capture sparseness. And then a crucial idea would be to use the fractional PRG approach of CHHL. And a very nice fact that we're going to use is the fact that sum of independent Gaussian is a Gaussian by itself, and this would allow us to think of this Gaussian distribution, instead of just one sample, we'll think of them as the sum of many samples and of very tiny vectors. And this will be very useful for the analysis. Okay, so this is just like a teaser, and let's see the actual details of the proof. Okay, so we are talking about bounded depth circuits, just to make sure that we are on the same page. We are talking about circuits where we have ANDs and OR gates. Each one has unbounded fan-in. We'll capture by S the number of gates in the circuits, and by D the depth, or the length of the longest path between input and output. In this case, the depth would be considered to be 3, because we have 3 gates from input to output. And the settings that we will focus in is where the size is quasi-polynomial, so n to the polylog, and the depth is a constant. The reason that this is the settings that we are interested in is that this is what happens when you simulate the polynomial hierarchy by AC0 circuit. So basically, you need to do, because you do something like 2 to the polylog n. This is like the size of the circuit when you expand, like you have there exists y of length polylog n. You go over all possibilities for this y, so this is the size that you would get. All right, so AC0 circuits are something that we know and love. And
how do you feed such circuits with real numbers?
Okay, it's not clear.
Okay.
Yeah, so it's a good question. We will come to it later.
Okay, thanks.
Yeah, so currently, yeah, it just works with, think of it in the Boolean domain. Okay, so what do we know about AC0 circuits? We know that they cannot compute parity. In fact, they require size exponential in n to compute parity, and this result was really motivated by giving an oracle separation, showing that P space is not in PH with respect to some oracle. In fact, these results mentioned this oracle separation in their title, and they introduced this notion of AC0 in order to solve this problem. So it's not, it's sort of not super surprising that when we talk about the polynomial hierarchy, we come back to AC0 again. And I want to mention one technique to prove this result, that parity is not in AC0, that sort of seemed to be like the wrong technique for our project, but in the end it will work. So this technique is a Fourier analytical technique. And basically, so based on a Hastad result, LMN showed that AC0 circuit can be well approximated in L2 norm by low degree polynomials over the reals. Okay, this is basically saying that they know something about the Fourier expansion of these circuits. On the other hand, parity cannot be well approximated by low degree polynomials. If you want to approximate parity even slightly, you need a polynomial of degree n. So this shows you that parity cannot be computed or even approximated by by AC0 circuits. But what's the problem with this approach? The potential problem is that the tasks that we are trying to separate between them are tasks for which quantum algorithm work, right? So quantum algorithm running in logarithmic time or polylogarithmic time, or making even a constant number of queries to the input, in our case, they work. And any quantum algorithm such as that also gives you a low degree approximation. So for any tasks that it solves, this task can be approximated by a low degree polynomial. So how can we differ between the two? So there is a difference. And the difference is that although both models are captured by low degree polynomials, these low degree polynomials are of different flavor. So the quantum part can be very very dense, and the AC0 approximation is always sparse. Okay, so in particular, in the example that we had before, we had a very low degree polynomial, phi, of degree 2, but if you look, the number of monomials is n squared. Okay, so almost maximum. And it doesn't seem that we can sort of like approximate it by a sparse of this set. However, this earlier result from 4 years ago that actually was motivated towards this project, we showed that AC0 has sparse low degree approximation. So we can write it in this Fourier notation that if you look at all the coefficients of sets of size k and we take the sum of their absolute value, this is at most polylog raised to the k. And you can also translate it into a result saying that you have a low degree polynomial that approximates your function. And if you look at how many coefficients you have at the kth level, it's polylog to the k. So you can sort of trim out all the coefficients that are smaller than some threshold, and then you would have at most polylog to the k coefficient in the kth level. Okay, but we will mostly use this, this bound. And with this bound, we thought we have a very straightforward approach how to show that the Forrelation is pseudorandom. And let's see this approach, and we'll see why it fails. Okay. So first attempt, and by the name you can guess how it will end up with. So we are trying to. Okay, so we are looking at a Boolean function. We are expressing it in the Fourier basis. Okay, so we are writing f of x as a sum over all subsets of the coordinates. We have a coefficient for each subset times the monomial. Okay, so we basically write a Boolean function as a multilinear extension, as a multilinear polynomial. Okay? What is nice about this creature is that now we can plug in values that are non-Boolean. Okay, so this is exactly what you asked. We can even have a nicer interpretation for this. For example, if we plug in, so remember that the inputs, that the Boolean inputs are plus and minus 1. What if we plug in the all zeros vector? Then we get the empty Fourier coefficient or the expectation under the uniform distribution. If we plug any other vector, let's say z1 to z2n, and think of them as numbers in like minus 1, 1 to the 2n, and what we will get, by multilinearity, we would get exactly the expectation of f on a vector of conflicts where these are the biases. Okay, so this is very related to how we defined even the distribution. Okay. Okay, recall what is our goal. Our goal is to show that the expectation of f on z prime, where z prime is sample according to d, and this is a distribution over Boolean strings, so this, there is no confusion what this means, is similar to the expectation of f under the uniform distribution. We want to show that like the difference between the two is something like 1 over square root n.
Avishay, this x is not the x before, it's now at 2n, length 2n.
Yeah, it's 2n, yeah, sorry. Yeah, just, yeah, I'm abusing x, I guess. Yeah, it's not the x from before. Okay, I want to recall how did we sample z prime. So we sampled z from g, and g is written there. And then we truncated. We made all the zi's to be between minus 1 and 1. And then we sampled independently coins with these biases. Okay. I claim that this gives me a very nice way to rewrite this thing. So using multilinearity of f and the fact that we are doing this process, we can show that this thing equals this thing. Okay, the expectation under d is the same as the expectation under g after applying the truncation. And why is that? You can see that it works for even if you fix the value of z. Fixing the value of z, you have this process where you sample independently, and then you basically want to show that the expectation is the same as the value of the multilinear function on this vector. And basically you can show it one monomial at a time and then use linearity of expectation. And for each monomial, you just use the fact that, for independent random variables, the expectation of the product is the product of the expectations. So that's really just a manipulation. So there's really equality between the two of them. What else do we use? So we want to use the fact that z is equal to the truncation of z with high probability. And recall that we picked the parameter such that this would happen. And then basically we want to like move from the truncation version to the real, like the actual version. Okay, so what does it tell us? It tells us that this distribution, this expectation is very similar to this expectation. So we can sort of swap between them and just prove that the expectation of f under G is very similar to the expectation of f under the uniform distribution. Okay, so this would be our goal now. And we are in the first attempt, so something would fail. So let's wait what would fail. So we are doing the most straightforward thing. We are just writing the the Fourier expansion and bounding it term by term, bounding this difference term by term. Yeah. So we are going here over all subsets. We have some coefficient for the subset. We have the expectation of the monomial under G minus the expectation of the monomial under U. Okay, what happens to this expression? This becomes 0 for most monomials, right? This is a uniform distribution, so this expectation would be 0 for almost all monomials except for the empty set, right? For the empty set, it will be 1. And then for the empty set, this will be 1 as well, so they would cancel each other out. So basically, we are left with this guy only for sets which are non-empty. Okay, and now what are we going to use? We're going to use the fact that these are Gaussians with 0 means. And this basically tells us that we can ignore all the odd degree terms. Okay, so for Gaussians with 0 means, all their odd moments are 0. This is a well-known fact about Gaussians. Okay, so now I'm using some estimation on these moments, and I bound each of these monomials by something like epsilon to the L times L factorial divided by square root 10 to the L. So I'm using some formula on Gaussians in order to do that. Let's not get into the exact details how I'm doing. And now, what do I have here? I have the sum of absolute values of Fourier coefficient of sets of size 2L. So I will plug in the bound that we mentioned before. So this is at most polylog n raised to the 2L. And what happens? Let's see. So for L equals 1, I get something like polylog squared times epsilon times 1 over square root 10. This is exactly what I wanted to prove. Okay, so the L equals 1 gives me what I was aiming for. L equals 2 seems to give me even something better. Polylog to the 4 times epsilon squared times 2 divided by n. So even I'm dividing here by n, so it's even better. However, at some point, so if I look at the first square root 10 terms here, the contribution is epsilon times polylog divided by square root 10, which is exactly what I wanted to prove. However, I don't know how to handle the high coefficient. I don't know what to do when L is really big, bigger than square root 10. And I think, in fact, you can probably, I think that you can show for this specific distribution that there are a large set with not so small coefficients. Okay, but so somehow something else, some other argument should work if we believe that the statement is correct. So one way to try to solve it is to apply noise to the distribution, but the problem with this approach is that it would also kill the quantum algorithm. So we were stuck on this for something like 4 years. And then after seeing this very beautiful paper on these fractional PRGs, we had these new ideas that made us go all the way. Okay, so I want to now state the main technical lemma. And I want to sort of abstract what we are doing, so we can sort of like forget all the parameters that we talked about so far. We just focus on what's written on this slide. So let's say that Z is some multivariate Gaussian on this dimension with these two properties. The variances of each variable is at most 1 over log n. Recall, why did we want that? Because we wanted with high probability the random variable Z to be within, all the coordinates to be within plus minus 1. Okay, this ensures that. So that's the only reason actually that we're going to ask for that. We also ask that the covariances between each two coordinates are small. So we are quantifying it by delta. And recall what was delta in our parameters. It was something like 1 over square root n. Okay. Then, any quasi-polynomial size constant depth circuits has this following distinguishability advantage. The advantage is at most delta times polylog n. Okay? I must give credit to Boaz and Yarek. They gave a very beautiful blog post on this, and they presented like the technical part in this language. So really this presentation is using their abstraction. Okay. I want to mention which properties of AC0 circuits I'm using towards proving this technical lemma. So the one thing that I'm using is a bound on the sum of absolute values of sets of size 2. Okay, I'm using the bound that the sum of absolute values of sets of size 2 is at most polylog n. Notice that I have a bound for all k, so for all set sizes, but I'm going to only use this bound. And the other thing that I'm going to use is the fact that AC0 circuits of certain size and certain depth are closed under restriction. So if I'm restricting, I'm getting a circuit of size which is at most s and depth which is at most t. Okay, so this is fairly simple property to satisfy. In other words, the proof could generalize to any class of function that has these two properties. And I will mention this in the new direction and open problems fact. So you can ask whether or not this bound in particular holds for larger classes of Boolean function. In particular, one that we suspect for which it would hold is AC0 circuits with parity gates.
In the first inequality, shouldn't it be greater than?
No. So we are not trying to get to a point in the cube. We're just trying to show that it's pseudorandom. Yeah, but it will be roughly this, so it will not be too far from that. Okay, so basically we want variances to be not too big, and we want the covariances to be small. Okay, that's all. Okay, so what will be the idea? The idea will be to view this Gaussian sample as a result of a random walk. Okay, so instead of sampling z according to g at once, we're going to sample t copies of z, z1 up to zt, independently, and then take their sum. So these are vectors, so we are taking the sum of these vectors and divide it by square root t. If you check, it will have the same means and the same variances as the original z. So basically, this is just a thought experiment. Okay, so this is one thing that is a bit different than what Kaveh was talking about. We are using this random walk only as a thought experiment. And another thing is that we are not doing this polarization. So we are not like changing the step size. We are like always taking the same step size. And we sort of making the walk not go for too long so that we would not go outside the cube. Okay, so that's what we are trying to do. Okay, so this idea was based on this recent paper of Ishan, Puya, Kaveh, and Chachar. And you will see that we are heavily using also a lemma that
But Avishay, T will be polylog, we should think of T as polylog.
Okay. So you should think of it as poly n. This is what I'm writing in the next slide. But actually, you can think of it as big as you want. You can think of it as a Brownian motion. We just didn't write it in this line. There is one thing that you need to change, but we already wrote it and published it online like over the weekend. So basically, you can think of T as large as you want. Okay. So we are trying to analyze this process. And we will use this random walk, we will use a hybrid argument in order to analyze it. Okay, so we will basically want to show that, so we have this starting point, the origin. and we are making t steps. Each step is pretty small. We will show that the expected value of f on h0 is very similar to the expected value of f on h1. We will show it for each two of these hybrids. And this will basically give us, by triangular inequalities, the fact that this is a pseudorandom. Okay. So again, we'll define h0 to be the origin. For I between 1 and t, we'll define hi to be the sum over the first I z divided by square root t. And then we will observe that ht is actually distributed according to the distributions that we are talking about, g. If you take t to infinity, this would give you a Brownian motion. My talk would not be in this language. So I'm just thinking of t as like poly-n, and this would be big enough. Yeah, probably we could have picked even t to be polygon for this application, but for the AC0, but maybe not in this bound that only uses the second. Okay. Okay, so in order to finish the proof, we just need to show that the expected value of f on the I plus 1 hybrid is very close to the expected value of f under the I hybrid. Okay, so just to show a hybrid argument. Right? So we will show that this is at most delta over t times polylog n. And why is this enough? When we are summing these t hybrids, we will get that the difference between the first and the last is at most delta over t times polylog times t. Okay, so delta times polylog. Okay, great. So this is the only thing that we are left to prove. And let's look at the base case, the difference between h0 and h1. This turns out to be very, very similar to our failed attempt. Okay, so basically what we're analyzing here, we're analyzing the difference between expected value of f on z divided by square root t minus the value of f on the all zero vectors, or the expected value of f on the uniform distribution. So basically you can write the same calculations that we did before, like expand the Fourier expansion, write an estimate for each coefficient. The main difference is that you divide each entry by square root t. And think of t as really huge. So this gives you obviously a lot. What it does is it gives you like an extra factor of square root t to the 2l for each coefficient of a set of size 2l. Okay? So this is the expressions that you get. Let's try to see what it gives you for sets of size 2. So for sets of size 2, you get L equals 1, so you get here a polylog. You get L equals 1, so it's delta times the constant divided by t. Okay, so you get delta over t times polylog n, which is what we want.
So the main difference is that earlier you had square root n to the L, now it's t to the L, and t is very big. So
yeah. So I think previously we didn't have this at all. And square root n was the delta, so delta was 1 over square root n, but yeah, so square root n was not enough, but n or n squared would be enough. Right, so basically, if we look at coefficient of sets of size 4 and beyond, then this t really kills them off. And this should not be super surprising. Basically, it's like applying a lot of noise on a function. When you apply a lot of noise to a function, basically you make it a low-degree polynomial, and then it's easy to fool it. So this is sort of what we knew 4 years ago. The main idea was to sort of do these many steps, not doing only one step. Okay, so the next idea is to reduce the general case to the base case. And we're using this very beautiful lemma of CHHL, and it's actually pretty simple to prove. It tells you that if you look at some point, and think of it as like where you ended up after I steps. So Z0 is like a point in the cube, and with high probability it will be, all the coordinates will be between -½ and ½, let's say. So bounded, a little bit bounded away from the edge. And look at the difference of f of z plus z0 minus f of z0. So apparently you can write this, it's a function of z, you can write it as the expected value over random restrictions of the restricted function on 2z minus the restriction function on 0. So basically you can you can show that if around 0, when you take a small step, you don't change the value by much on the restricted function, then around any point, you don't change it by much. Okay, so basically it's like relating like the derivatives of this multilinear polynomial at a certain point to the derivatives of a restriction at 0. And then to apply our base case on the restricted function. Okay, so basically once you have this lemma, it's very simple to use it in order to show that the difference between the I+1 hybrid and the I hybrid is small. So we just condition on the value of the I hybrid, and we condition on the fact that also it falls within this smaller cube. Yeah.
What is the relation between the number of bits you fixed and t? The random restriction.
Yeah, so the random restriction here, okay, so the random restriction will simply want to move like, so it's like what Kaveh mentioned, right? So you have, let's say that you have this, sorry. So you have this, cube, and now you are like here. So basically you want to look at this cube. So you want to sort of shift this cube to a cube around 0. So then you take random restriction. So it's actually the random restriction only depends on this Z0. Z0.
And
it doesn't depend on.
But it's roughly the number of set variables is going to be proportional to the sum of the absolute values of the coordinates at Z0.
Yeah.
Yeah. So basically that tells you the probability of flipping that coordinate.
Yeah. Yes. Okay, so now we want to measure the difference between the I+1 hybrid and the I hybrid. So the I+1 hybrid is just the I hybrid plus a small vector. And then we are using this lemma to relate this to the difference between the restricted function on 0 and the small vector. And then we use a base case. And we use the fact that f is closed under restriction. So basically we use the base case on f rho. Okay. So this is actually the entire proof. Yeah, so it's a good point to.
So in the lemma you use really choose this Z0 instead of Z, just trying to map the candy region.
Yeah, I'm like multiplying here by 2.
So in the lemma, it's the expectation.
So here, like, right? So here I'm taking Z, and here I'm like multiplying by.
For
all the vector, like all the coordinates. And sort of it's, yeah. There's a very short proof for this lemma, like a few lines, maybe not today, but if
it's just 0 lines, I think.
0. Okay, so maybe.
You just, yeah.
Yeah, it's okay. It's an let's say that it's an exercise, but it's a very useful lemma. Okay.
I think the question was syntactic. When you apply the lemma, syntactically it seems that you don't. So Z0 is HI, and Z is whatever, and you. When you apply, so it seems that syntactically the lemma does not imply this inequality.
So maybe here you should think of like when I'm computing it, this difference. Think of it as like I'm fixing the where I am at after the ith step. Then I'm sort of fixing a vector Z0. I'm conditioning on the event that this vector is also lies between -half and half. And then like you can replace HI by Z0 in every place. And then it's only a function. It's a function only on the Z on this ZI+1, and you should replace this with Z. Okay. I'm pushing under the rug okay, the fact that this happens with high probability, but what happens if it doesn't happen? So you need to sort of handle also this case, but yeah, at least like at a high level, this is what's going on. So there was a lot of text on the slide, so let's just do a proof by picture, like a recap of the proof by picture. So we did this random walk of many tiny steps. And then we used very simple Fourier analysis to show that the value of f changes by a small quantity when you do the first step. And this remarkably only used the second level of the Fourier expansion. And then we use this lemma of CHHL to relate between the ith step and the first step. Sort of to say that they are almost the same, but we need to make sure that the functions are closed under restriction. So we are going, like we're relating the ith step on the original function with the first step under a restricted function. Okay, so this is basically the scheme of the proof. And let's recap what we did so far. So we defined the distribution over Boolean strings based on the multivariate Gaussian distribution G. We showed that it was not pseudorandom against a quantum algorithm running in logarithmic time and making one query. And the main part of the main contribution of our work was to show that this distribution is pseudorandom against AC0 circuits. And we had these thought experiments of instead of sampling Z at once, we sort of did this thought experiment where we sampled a lot of small, tiny vectors, summed them up. And in order to analyze the first step, we used the fact that AC0 circuits are well approximated by sparse low-degree polynomials. Okay. And in order to reduce the general step to the first step, we use this lemma of CHHL. Okay, so this is almost all the details, all the interesting details going on from the proof. So I want to go now to open questions. So following up our results, Aaronson and Fortnow came up with an oracle under which P equals to NP. And in particular, if P equals to NP, then the polynomial hierarchy collapses and everything equals to P. However, BQP has some things that cannot be done in this polynomial hierarchy. So you must first separate BQP from the polynomial hierarchy in order to have such a result. It requires a little bit more than that. So basically, you can say, even if in the unexpected world where P equals to NP, maybe quantum computers would have still problems that cannot be solved efficiently. Classic. Lance also showed that under the Forrelation oracle, pH is infinite. This was known for other oracles, but I think it's interesting, and it's also true under this oracle. They pose some open problems. So one is that we still haven't been able to show that the original suggestion of Scott works. So the one where we took the signs instead of thinking of them as biases of coins. Another is to come up with new oracle separations that are sort of as a prerequisite, that have as a prerequisite this BQP versus pH separation. So these basically are things that are false for BPP, and they think that there might be oracles for which they hold for BQP, both these questions. But I want to mention another open problem that I already hinted. So you can try to use this framework to separate BQLogTime from AC0 with parity gates. And the only place where you need to change the proof is that you need to prove a Fourier bound on AC0 with parity gates. And what suffices for the proof to work is that the sum of coefficient of sets of size 2 is at most square root n over polylog n. We conjecture actually that the right bound is much better than that. We conjecture that the right bound is something like polylog n. Currently, actually, we can prove something like square root n times polylog n, so we are very close to the border. And we showed in this work with Ishan, Puya, and Shachar, that we just posted online, we showed that if you can prove this conjecture, then you can sort of de-randomize the argument that I showed you here and get an explicit PRG based also on the polarizing random walks, with seed length polylog n, fooling AC0 with parity gates. And just as a comparison, the state-of-the-art seed length for AC0 with parity gates is something like n minus n over polylog, so more than linear in n, so like almost n. So if you just prove this small conjecture, you would improve from n to polylog. So I want to end with that, and thank you so much.
Questions for Avishay?
So it's kind of counterintuitive that you try this argument where the first attempt that failed, but then you just broke it into small parts and used the triangle inequality, which would be worse, and then it worked. So why do you have some feeling for why that's the case?
I mean, I'm not sure. I mean, basically, we couldn't handle like the high coefficients. Like we didn't know how they behave. One thing that you can try to do is sort of do Cauchy-Schwarz. So this works like under the uniform distribution. It doesn't work here. The sum of squares of the distribution that we were getting was like exponential in n, and somehow this failed. Yeah, I mean, it should have worked. I mean, it's true also for this analysis, but when we sort of write it term by term, and we couldn't found it. So I'm not sure that is a good question to try to reconcile this.
So the PRG that your conjecture implies, is that for large error or for smaller towards the error parameter?
So the dependency on the error of the PRG is bad. It's like polynomial in the error parameter. So in fact, this PRG would not imply strong correlation bounds, just PRG.
Which is nice, I guess, more promising.
Yeah, depends. Okay, depends on how you view things, optimist or pessimist.
So yeah, just to say again that we're in the market for both short communications and for open problems. So if you have kind of a short talk to give about a recent result, contact Ben about it. And if you have an open problem to present, email me about it. Let's thank Avishay again.